Alright, so we are in section 14.3, and in one of the classes anyway, I didn't get through this part. So implicit partial differentiation is something we need to talk about. And just review from Calc 1, when we're of implicit, or just regular implicit differentiation. So we'll go over that first. And so if we're asked to find the derivative of y with respect to x, given an equation that doesn't have y solved for, usually you can't solve for y. Just appreciate that for a second here explicitly. So we're kind of stuck with this equation with y's on both sides, or not being able to solve explicitly for y in a good way or a way. So we're stuck with this. So what you do with implicit differentiation is kind of a backdoor approach where you take the derivative of both sides with respect to x, and then we have to treat the y's in a special way. And so notice here, when we encounter y cubed, y implicitly depends on x, and so we can treat it sort of like a f of x, which is unknown, and you need to take its derivative in that way, treating it as such. So when we take the derivative of f of x with respect to x, then we need to use the chain rule potentially for the inner part of that function if it's a composite function. So we treat y as like a hidden composite function in terms of x. And so when you take its derivative with respect to x, you take the derivative with respect to y, or it would be like analogous to taking the derivative of the outer function of a composite function, and you get 3y squared. And then you need to remember to multiply by dy over dx, and that's because in the chain rule we multiply by the inner function. And so this is saying, okay, now that inner function is y, we need to take the times the derivative of that, or times dy over dx. So the rest of these are the rest of the side is really easy. X squared, its derivative is 2x, and then I did have a typo here and I had minus. I have no idea why. Change to plus here, of course. And then taking the derivative with respect to x on the right-hand side, the derivative of x is, with respect to x, is just 1. And the derivative of minus y is not, it's just hanging out by itself there. It's not like y cubed, or it's not ln y, or sine of y. So here, it's just y. So you take its derivative with respect to x, which is simply dy over dx, and the chain rule is not needed here, plus the derivative of 1 and 0. So once you do that, the hard work is done. Now you just treat dy over dx like some variable, and you do the algebra to solve for it. So I'm going to try to get these on the both sides, same side, by adding dy over dx, bring that over, and then shift over minus 2x. On the right, factor out the dy over dx, and then I have leftovers inside 3y squared plus 1. And then I'm just going to divide by that parenthesis thing to solve for dy over dx. So it's like a backdoor approach to finding the derivative of y with respect to x. Even though we couldn't solve for y explicitly in terms of x, we can still find the derivative of y with respect to x in that way. So we're going to use this same type of method for implicit partial differentiation, but there's going to be a twist because we're doing partial derivatives. Alright, so let's say we want to find the partial derivative of z with respect to x, given x cubed plus y cubed plus z cubed plus 6xyz equals 1. So can't solve explicitly for z, and so it would be nice if we could do this implicit differentiation technique and find that partial derivative of z with respect to x in that way. So it turns out we can do this. Something important to note from the beginning here, in the context of our partial derivatives, so far we've been saying, oh, okay, we take a partial with respect to x, everything's a constant, or technically it's held fixed, and so we can treat it like a constant and take its derivative, and it's way easier. But in this context, because we are taking the partial with z with respect to x, z implicitly depends on x, and we got to treat it like a function of x. So that's going to change things a bit. However, y is not being treated special in that way. So we just treat it like we did before as a constant when we were taking partial derivatives with respect to x. So noting that, we take the partial derivative on both sides with respect to x. The partial with respect to x cubed is 3x squared. Simple. Y cubed in this context is just holding it fixed, and it is 0. Okay. Actually, I'm working left to right here, so there's a 0. Now this is a little tricky. Z cubed in this context is not 0 for the derivative with respect to x, partial. So, I know a little confusing, but the y above in the review, this is like the implicit function in terms of x. Was the y up here, now it's a z. And so it's, you can think of it as a hidden function of x or a hidden dependence on x. And so we got and then it's cubed, so it is like an inner function and a composite function. So we take this derivative similar to how we took it in the review example with the y cubed. It's going to be 3z squared times del z over del x using the chain rule. So moving on, we have plus 6xyz. So here we got to think hard. We are doing this partial derivative with respect to x. We got a yz hanging out here times y we can treat as a constant, so it's sort of like 6y out front. X is a variable, z is implicitly dependent on x. So in a sense what we have is x times like some sort of function of x kind of thing. And so we need to do the product rule here, and the 6y can be left out front as a constant multiple in this context, and then using the product rule we have our x, not taking the derivative of that, and then taking the derivative of the other thing, which is z. So del z over del x, it's just z by itself. So that's its partial derivative with respect to x, then plus plain z times the derivative of x with respect to x, which is 1. Okay. The derivative of the right is 0. So the hard work is done. Now it's a matter of doing algebra to solve for del z over del x. So treat that as a package deal. Notice that you'd want to distribute the 6y to free up this term right here with the del z over del x. Now you can group these two, factor out the dz or del z over del x, rearrange, put the other junk on the other side by subtraction, divide, and you're done. Finally, we're going to briefly talk about some applications of this. There's a whole course called Partial Differential Equations that's taught at the upper division / grad level in the math department here, and this is where you would talk about solutions to partial differential equations. So not something in ordinary differential equations class that you may have taken. And so we're not doing the solutions to the partial differential equations, but we can at least talk about whether a function satisfies a partial differential equation. And so that's what we're going to do. So there's a list of equations here, partial differential equations, that occur a lot in physics, geophysics, because they're something that fit with physical properties of some things like waves and heat. So these are, conditions that have to be satisfied, and if we have this equation holding, then we can use it for an equation that's representing different things like temperature and satisfy these conditions. Alright, anyway, rambling. So you don't need to memorize any of these. You'll be given in the context of a problem, and we'll see an example here on the context here, what you would need to do with these. But there's Laplace's equation, which is a 2D and a 3D form, which says the partial of the output u with respect to one of the independent variables x, the second derivative of that, partial derivative of that, second partial with respect to the other variable, and then you add them, you have to get 0. And so then same deal with 3D, and you just add a term. So some related equations are the wave equation, A is a constant in this one, and that depends on the parameters of this situation you're looking at. Then the heat equation, there's also something called the diffusion equation, which is related here. Our diffusion equations are solutions to these. So we have our big T sub T, so this, remember, is in context is a partial derivative of temperature with respect to T, where T is time. K is a constant, and then T sub XX is the partial twice with respect to X, which is denoting depth. Alright, so anyway, I have a geophysics degree, and these are equations I actually used in some of my coursework. In a study of frost penetration, it has found that the temperature T, at time T measured in days, at depth X measured in feet, can be modeled by the equation T of xt equals T naught plus T sub 1 e to the lambda x times sine to the omega T minus lambda x, where omega is a constant and lambda is also a constant. So finding our partial big T with respect to x, you can go ahead and do this. It's a little distracting with all these variables in here, but notice it's delineated pretty clearly here that the real variables are x and t. So T sub naught is a constant. We don't know what that constant is, but it is a constant. It's not a variable. It's not varying as a function. The temperature is not varying as a function of it. It's just some value you plug in, whether you know it or not. It's a constant. Same with T sub 1, same with lambda, same with omega. So notice that then it's just t's and x's, and you need to try to focus on that when you're taking this partial of big T with respect to x. So T sub 0, its derivative is 0. T sub 1 is a constant. You can start nesting in here and looking at what remains. You have e to the constant x, sine with a t and an x. So when we take the partial with respect to x, then we got two functions with x's in them multiplied. So you need to do the product rule, which I showed here. This one involves also the chain rule for this derivative of the sine thing, and then also for the derivative of the e thing. Alright, so you simplify that, and you can factor out lambda, and then also e to the negative lambda x and a negative, so there it be. What is the physical significance? One way to state it is the rate represents how the temperature varies as a function of depth at a particular time t. Okay, next thing is doing it kind of switched up with our partial with respect to little t. So when you do that, it's easier because we have this e to the whatever thing x, and that is now a constant, so just group that with the T sub 1, and then here we employ the chain rule. You get an omega out front from that, and then take the derivative of the outside, you get cosine. So this rate represents how the temperature varies as a function of time at a particular depth x. Okay, so I added more parts here, but actually we're not going to do dd. It's getting a little carried away after we do those. So part C show that T satisfies the heat equation. Big T sub T equals KT sub XX for a certain constant K. So this is something that we need to explore a bit more. How would you do this? There's different ways, but you know how to find these partial derivatives, and that's the first step. So we had this original equation for big T, and if you take its partial with respect to little t, you get a result, and we actually already did that in part B. We need to also figure out what T sub XX is. We already have T sub X from B, just take another partial for that, and then unfortunately we have to do the product rule again, which is sort of a colossal mess here. Now what? So let's assume that this equation is going to hold, and we can find k, and k is a constant. Well, if that's true, we're going to be able to find that k, and then that k is going to be truly a constant. It's not going to be dependent on t or x. So we can just go ahead and do that. Another thing is we got this mess with t sub xx. It's like a total mess. And it doesn't look a whole lot like t sub t. And these things should kind of look similar. I mean, this one only has a cosine with t and an x in it, and like we got all these sines and cosines all over the place. And we need to simplify that, in other words, to kind of, before we can start finding k. Some things should cancel out or whatever. So doing some stuff with t sub xx initially to kind of make it a little bit prettier, make it look better. So then you can notice things like, oh, I got like terms with the cosines, it's 2 with them together, just like x plus x is 2x, as we got 2 cosine omega t minus lambda t x. We get an unfortunate thing with the sines summing to 0. So then it actually boils down to something that kind of looks like t sub t. So again, solving into that equation there that was given, the heat equation, then, and having k in here, we can solve for k now. So all this variable stuff, fortunately, cancels out, and then we solve for k and we just get omega over 2 lambda squared. Because omega and lambda are constants, and then obviously 2 is a constant, then what we have is a constant. And so that means that this wave equation held, and we found the k that we were supposed to. So that's it. Don't have to memorize those partial differential equations. It's just, you know, being able to do a problem like this, or maybe even a little bit simpler. That's it.